Um, Thank you very much. And I think we will go to the next speaker, who is Mr. Ken Visser. And well, Ken Visser, I know it's very early morning in US right now. So thank you very much for getting up that early. So, but I see here on the screen that you got a cup of coffee. So yeah. Ken, are you ready to go on the screen now?
I am ready. I will share my screen.
Thank you.
And,
welcome.
And let me know. Is this good?
Yes, looks good.
All right. Well, thank you very much. My name is Ken Visser, and I am going to talk a little bit about some of our efforts here in upstate New York, for those of you who don't know where we are. And I'm actually wearing two hats. I teach here at Clarkson University, and I've been here for over 20 years. And my other hat is for the company that we've started, which is called Ducted Wind Turbines. And so that's kind of, this is a little bit of a story of really taking technology from the lab and trying to commercialize it. And I have to say, you know, we have a lot of interesting projects here at the university, but we've been doing a lot of different wind things, and eventually you can either let it sit on a shelf or you can try and make it happen. And so we've decided to see if we could commercialize some of the stuff we have uncovered here, and hopefully this will give you some inspiration as well. But it is really a story of the challenges that we're facing, and we're in the middle of them right now. So that's also part of the story. Okay, let me get started here. So this is my agenda. I will have a little bit of a background to kind of give you an idea how we got to this point from our research at the university, then how this company formation started, which I must confess, at first we didn't think we were going to have a company, where we are in terms of field testing today, and then how we're moving forward. So there is a challenge to small wind, as you all know, and I've put a picture up here of my colleague Mike Berge's 1kW machine, kind of one of the groundbreakers essentially in this business. But there is a lot of challenge. There's a high unit energy cost in terms of cost per kilowatt hour. There's a high capital cost, especially to the consumer. There's generally a long return for your investment, sometimes up to 20 years. That's also dissuades people. And maybe in the last decade, we've been undermined by solar a bit too, because the cost has come down a lot. And so all of these things present quite a challenge to try to commercialize the technology like wind, especially small wind, of course. So I've been at Clarkson University for about 20 years, and we focused on trying to increase the energy extraction for small wind turbines. We've looked at a lot of different things. Lower noise. Noise is always an issue. And of course, this is a design problem with a lot of aspects. So acoustics take a big play. You can drop the noise if you can lower the RPM. Reduced furling, we've looked at that. How can we extract more energy? We've looked at different kinds of airfoils, in particular how to reduce the cost with flat plate or flat curved airfoils, which is a much cheaper cost. And how can we extract energy at higher and lower winds more than what is done today? So all of these kind of things are just some of the things that we've looked at. Really, we've kind of been focusing on opening up lower speed resource areas. If you think about wind resource, there's a lot of lower speed resource areas that aren't utilized. And if we can somehow utilize them, we can increase the distributed energy generation that we can generate here, both of course here in the States and around the world. We like to use real world metrics, and it's one thing to improve the technology, but if it costs twice as much to get twice as much energy, you really haven't pushed the real world metric. So our metric is the cost per unit energy. That's what we use, which means a couple of things. You can reduce the cost to have a less expensive turbine, or you can improve the energy output to make it more efficient and improve the overall transfer from the wind energy to the electric energy. Our target when we started this was to try to reduce the cost per kilowatt hour by a factor of 2 from what the current market was. And this was probably, I wouldn't say 20 years ago, but maybe about a decade ago we started on this. Our current focus is on a ducted wind turbine. Most of you have probably seen this technology before. It's not new. In fact, I think the oldest one that I've seen in the literature is about 100 years old. And the concept is fairly straightforward. Instead of intercepting a certain amount of energy noted there by A1, you can capture a larger mass flow if you put a duct around the turbine. So that's really the basics. I'm not going to get into all the details. A lot of work has been done on this, both theoretically and experimentally around the world. But we really wanted to take a look at this and see, is this really an economically viable, a commercializable, if you will, technology? There's advantages and disadvantages to these kind of turbines. They can open up lower wind speed areas because they can capture a bigger mass flow for a given wind speed. So that was one of the things that attracted us. They have a smaller visual, and you can play that off for diameter or for height, because you can have a smaller turbine to get the same energy output. But there are certain disadvantages, of course. Now you have to have a shroud. That increases the cost and increases the complexity. And that also increases the drag force, which tends to increase the structure weight and can also increase the tower and foundation weight. So it certainly has pros and cons, and these need to be traded off against each other. The question, of course, is this a lower cost per unit energy solution or not? And that's the overriding question. Why are we different than all these other ducted turbines? Well, this comes out of some of our research here that we've done at Clarkson. Over the years, we've noted that most people put the rotor at the throat of the duct, because you might say, well, that's where the highest speed is, and its power is proportional to the cube of the speed, so that's where I would put it. But the thing is, once you put the rotor there, it's no longer the location of the highest speed, and so it's actually detrimental. So it's not that it doesn't increase the mass flow rate, the duct still does, but you don't extract as much energy as you can. So we found if we move it aft, we can increase the energy output. The second thing we noticed is that, at least, and I've never seen anybody do this before in terms of documentation, is that once you put the rotor in a duct, it no longer sees a uniform velocity flow stream. And so you have to design the rotor in the presence of the flow field that the duct imposes on the rotor. And that's a non-uniform flow field. And that's very important, because that incoming flow field plus the rotational speed sets up the twist distribution that you need on the rotor. So you can improve things. You can have a better twist distribution for a rotor operating in a duct. So we have a patent on that from the university here, which I guess eventually came out last year. Those things take a while to come out. And so, and that's where we sit from the technology point of view at the university here. So our strategy to design something like this is kind of a hybrid strategy. We use some CFD to determine what the flow field is, and we use just an actuator disk for the duct, and then we use that with our tuned BEM code to develop a blade profile and twist distribution, and we combine them to get a design. And I won't go into any of that today, I don't have time, but if you go, I can certainly send you some information on that if you like. So at this point, we decided, you know, maybe, well, the next section here is on company formation. How did this all come about? We decided we needed a prototype. We needed to see if we could test this. And the state of New York had an energy incubator program called Nexus New York, and we applied to that, and we got some money from them, enough essentially to build a prototype. And so we decided that we would build a small little prototype and compare it to what the Berge XL does. And so we designed it with the same diameter, some different other parameters for tip speed ratio and a different blade. I won't go into that today, because that's not really the focus. We built one in our lab. You can see here, this was the mock-up. And we actually machined some aluminum blades, so we would see how, if this was the best case scenario. This obviously isn't something for commercial production, but we just wanted to see if we could validate what we were seeing on the computer. And I went to the University of Waterloo on the other side of Toronto, Canada. I have a colleague there, and he has a big facility. And so we did some testing there. This was in 2015, 2016. We took a look at the open rotor configuration. We took a look at the ducted configuration. You can see it's kind of an open chamber wind tunnel. And the results, we saw some encouraging results. You know, with the duct on our rotor, we saw almost twice what the Berge XL was doing. So that was encouraging. Of course, it was in a wind tunnel. We understand that. But it was enough to say, you know, there might be something here. Perhaps we should build one for the outside, for the ambient conditions. There's still an outstanding question, of course, is this economically viable? And there's really no point in moving forward if it's not. So we compared our turbine to other turbines of the same size on the rotor. There's a 3-meter geometry there, 4-meter rotor, and those were our estimates. And of course, the costs were just estimates. That's all we had in those days. But we thought, well, you know, our estimates are in the green there. Even compared to the 6-meter rotors that were out there at the time, we were below that in cost per unit energy. That's what's running along the vertical axis here. So this was enough encouragement to say, you know, we might have something here. And, you know, our mission wasn't just to make something commercial so we can sell wind turbines. Our mission really is driven by improving the quality of life of people on this planet. And there's over 1 billion people that don't have electricity, and we can help that out. I think we can't just let the technology sit on the shelf. We have to get it out in the world. So we thought we would give this a try. As part of this Nexus New York program, when we were involved, they said, you have to make a company. This is kind of, believe it or not, what got our company started. So we formed a company, and we called it Ducted Turbines International. And now we had a company. And I did this with a colleague of mine, Paul Pavone. He's on here this morning as well, drinking his early morning coffee. And so where did we go from there? Well, now we had a company, so to speak, and the university where I teach at, they were very interested, and they asked if we could build a prototype. So we said, this is great, you know, we'll build a prototype if you actually buy it from us, from the company, because we're licensing the technology from Clarkson. And so we actually had our first sale, if you will, which was kind of encouraging. So we built one. And there were a lot of challenges to building this. So what do we use in terms of materials and components? And I'll get into that in a little bit here. But this was kind of, we'll call this the Gen 1. This was kind of our, I guess you could say, workhorse to try different things out. And a lot of things we learned. We made the duct out of fiberglass, hand laid up. We made all the different parts in the lab. And this was really a research turbine to see what we could do. And yes, we get a lot of snow here, so we can't stop for that. So we just continued to build. And this was in, I believe, the fall of 2017 that we actually got this up and running. This is on one of the buildings at Clarkson University. And it's actually designed to support a wind turbine. We're sitting on a bearing wall that runs right to the ground. So they said, well, we have a spot for that if you're interested. And so we did. So we built one there. It's a 3.5 kW machine. It has a 3-meter rotor and a 3.7 meter diameter duct. And this is it. I hope you can hear this. This is what happened after all that effort. And we finally threw the switch this morning.
Okay. She is running. It is. We released the brake. She's running. She's running. Check it out.
Kind of running across the ground.
This is great. Woo! All right. Gotta like that. You gotta like that. Okay.
So I don't know about you, but there is a certain sense of excitement when you finally get it going, and we were quite happy that it was even turning. You know, I mean, you have that kind of uncertainty. So this is our unit here at the university. We've been running it for 2 years now, and we use it as a workhorse. We test different kinds of things, everything from electronic systems to different blade designs. And it really is quite handy because I can just walk down from my office and check things out. And it's still running. If you're interested, you're more than welcome. We have a camera on it and a little bit of data that shows up. I think this is an older screen. We have some information from the electronics now too, so you can see how it's doing. And that's one of the things, one of the challenges with small turbines is their robustness and their longevity. And so we keep it running, and she's doing quite well so far. But now what? And so as soon as we had this running and we had this little company, which was an LLC, and people started finding out about this, we had some interest from investors. And where are we going to go with this? And what are we going to do with this? And how are we going to commercialize this? And so with all of that, we decided to kind of rebrand ourselves a little bit. We incorporated the company so we can handle investment strategies. We brought some people on. We have a CEO now, Joe Dixon. He's online here too this morning. And we actually became a real company. And then at that point, now we really have some challenges to think about, because what are we going to do about generators? What are we going to do about electronics? What are we going to do about towers? What are we going to do about materials? And it's one thing to build a research turbine, and it's another thing to try and see if you can actually build multiple turbines and commercialize the technology in a way. So now the challenges really started, and I'd like to talk a little bit about them. And maybe lots of you out there who have tried this or are building small turbines have good experience, and we're open for discussion, and we're learning along the way as well. So with generators, we started off with a Jinlong because I had some in my lab. but they don't make them anymore. So we looked all over the United States. We can't find a permanent magnet generator here at all. And so eventually we settled on a unit from Lancor in Spain. And so far, so good with them. Our contact is Eduardo there, and he's helped us a lot. And so that's our current baseline 3.5 kW machine coming out of Spain. Electronics, another big challenge. We were using an Aurora. All of you are, I'm sure, familiar with that. They don't make them anymore. So, you know, it's one thing, again, for a research turbine, it's another thing to try and commercialize a product. We've kind of teamed up with a company in Texas. They make an inverter called a Solarc. It's a solar inverter, but they are converting it into a wind inverter. I'm sure you all know the lack of wind inverter technology on the planet these days. So we've had a great partnership with them, been working for a year trying to work on that. We tried another system called Grief out of China, and pardon the name of the company, but that is their name. But in the end, it just caused us a lot of grief for a lot of different reasons I'm not going into today. But primarily it was transfer time on the Modbus for information. And right now we've also settled on a company out of Ireland that makes a unit called a Voltsys. Quentin is the company lead there, and he'll be speaking after me today. So I can just say good things about him, a little plug there, and combining that with an ABB 6kW inverter, which is now, of course, bought out by Fimer. What about towers? Another big challenge. We've been using Ambor towers, and those are our initial units. That's one of our units there that I'll talk about in a second. So far, so good, but you know, now we have to buy them from them, and they come from overseas in China, so it takes a long time to get here. Again, another challenge. We don't make towers, and we don't make a lot of these components, so it's really, you know, we have to find these components to support our design, and that is quite a challenge. What about materials? How do we make our duct? Our initial one was made out of hand layup fiberglass, not an option for commercialization. So we've turned to a rotational molding strategy. That's a rotational molding machine there up in the upper left-hand corner. And you have these molds, and essentially it's made out of plastic. And we've had some interesting challenges, but we've managed to create something. And just to kind of give you an idea, because cost per unit energy is our metric, our hand layup fiberglass duct for our Gen 1 unit at the university cost me $3,900. Well, what we can do with the rotational molding for the entire duct, once we get into production, we can build the entire duct for less than $600. So a big difference with the materials. Here you can see some of the prototype designs. There are some of the pieces. We're making it in quarters, an assembly there in our facility, and building one out in the open. Blades, another challenge. How do we make them? You know, molds are expensive, and how do you get that kind of cost, you know, amortized over the entire cost of your turbines, how many you sell? So we thought of a different strategy, and we thought maybe we could press them out of aluminum using a flat curved plate design, which works very well at low Reynolds numbers. And so here are the guys in the shop. Of course, we did a lot of experimentation and how do you make this and all kinds of different things. And I can't go into all the details here. But eventually, after many trials and error, we managed to press a blade, which was absolutely fantastic because we have both a curvature in the chordwise direction and a twist distribution. It's not an easy task. And here's the final blade. That's a picture of me with my daughter there, who's not an engineer, but still excited about this with one of our finished blade designs. So again, is this the final product? Well, not necessarily. Our first set of blades on the Gen 1 were carbon fiber, but carbon fiber costs a lot too. And so we're exploring this possibility as well, because a pressed aluminum blade is considerably cheaper. Okay, on to field test installations. Right now, we are setting up several different field test installations. We call them Gen 2s. We've received some support from the National Renewable Energy Lab out of Colorado. We were very gracious for that under a CIP grant, and they've enabled us to build 2 test turbines, but we've also built some other ones. And I wanted just to kind of show you a couple of them here. This one is at El Sable Forks. It's on a dairy farm. And it's been up and running since November. This is one at our turbine test site. This is one of the research turbines from our NREL CIP grant that we're testing. And this is at Clarkson at the airport here in Potsdam, New York. We just had some students out there the other day, so that was kind of, it's always great to be educating students that way. This is another one of our test turbines from our NREL grant. This is down in Intertech. This is about 3 hours south of us, about a half hour south of Syracuse. That's on a 20-meter tower, and it's undergoing, essentially it's a third-party testing at this point. And so we have field units out there. We hope to build somewhere around maybe a dozen Gen 2 field units to people who are interested. And they realize it's part of the research program. We're looking, you know, for showstoppers, anything that might jump out at us. And where are we going from here? Well, we now have a facility outside of Potsdam where we can actually build some of these, because we can't do any commercial work on the university. That all has to be off of university grounds. This is our current status today. We've raised some convertible debt, about $750,000. We have some letters of intent for over 300 turbines, which we certainly can't deliver on yet. We have an office and facility established. We're looking at distribution partnerships. And if you're interested in more information, you can certainly go to our website, and I'm certainly, you know, you can send me an email. I'm happy to answer questions at any time. I'd kind of like to end today with a little bit of a PR video that we have here. You know, once you get to a commercialization, it's always nice. And some folks volunteered their time to come out and take some video of our turbine out at Asgard Farm and Dairy. So I hope this comes through on the audio okay. I'll just let you take a listen.
One inverter, solar and wind. You can also hook a generator to that if needed, and you can hook energy storage, so you can be on grid or off grid. Just that whole combination is game breaking right now. No one's doing this. This turbine was designed at Clarkson University in Potsdam, New York. The duct itself, the shroud that's around these blades, about 622 iterations were done by a PhD student at Clarkson University. And our utility patent is the twist of the blades and how they're positioned in the presence of a duct. It's a 3.5 kW wind turbine, but it puts out twice the energy as an equivalent open-bladed without a duct. At 5 meters per second, it'll do 7,000 kilowatt hours a year. So it's equal to about 22 to 24 solar panels, the same price. It has a permanent magnet generator, which is all encased.
I'm sorry? Okay, I thought I heard somebody say something. I apologize for that. Well, I think my time is getting close to being up anyway. And so maybe this is a good time to end, and I can take any kind of questions that you like. And if you're interested, I can certainly give you a link to the video if you want to watch the whole thing. But it's kind of exciting. We're moving forward. And hopefully within the next 6 months, we get some good field data, and hopefully not too many showstoppers. And we can continue to push forward in this direction. Thank you for your time.
Thank you very much, Ken. It was very interesting. And maybe you could send us a link to the video so everybody can see the whole video.
Certainly, yeah. I think sorry about that, but I think I'm actually out of time here. So
yeah, but well, we a bit elastic as well. Anyhow, tomorrow afternoon there will be session 5, placement and design of small wind turbines, and that might be something connected to your project here and to your business case. It's just for information. But are there any questions right now in here for Ken Visser? Yeah, we've got 2, it seems. Yes. Hi, Ken. How do you see the public acceptance for such a turbine with a larger visual impact compared to a typical wind turbine?
So that's a really good question. And of course, when people hear that we're working on wind turbines or something, they immediately think big ones. And so, of course, when we tell them, no, this is distributed energy, it's behind the meter, it's smaller, then they become interested. But we have found very interesting, when people see a picture of our turbine, the first thing they say is, wow, I like how that looks. And I'm kind of surprised. I would expect more people to say, well, what's the performance? Because that's what my concern is. But we have got a very positive response in terms of aesthetics to how the turbine looks, despite the fact that there's, of course, more structure there than you would have with just an open rotor.
Okay, thank you. There's another question, and for how long, for low wind, what is your target rated wind speed, and how will it expand the market?
So I'm not sure I understand. We're right in terms of a low wind speed. You know, I guess the lowest wind speed that we're targeting is somewhere between 3 and 4 meters a second. I mean, the turbine starts up at, I don't know, between 2 and 2.5 meters a second. But, you know, of course, the energy is much lower at that point. But by the time you get between 3 and 4 meters a second, we're producing. And I think, you know, I don't know what the typical regime is in terms of making a decision of whether you want to have a turbine there or not. I think from a commercial point of view, I think for big ones, you have to be 6 to 7 or something like that. But we can certainly operate between 3 and 4. And yes, the energy and the power there is less, obviously. But remember, we're after energy. And so if you can even extract that over a longer time and having the turbine run, extracting all the time, then it's the amount of energy that's important, not exactly the power rating. So I guess I would say between 3 and 4 is kind of our low end.
Okay, thank you. And then there is one more question here. Oh, it disappeared from me. Here we go again. Where are you standing currently with the leveraged cost of energy? Did you reach your aim in reducing it in dollars per kilowatt hour?
So yeah, and well, in terms of getting to half of what was currently on the market, we certainly have. And so the question then becomes, what's the final cost? But I think in terms of being competitive in the market, absolutely. You know, I've had to learn a lot about trying to run a business and trying to get costs and materials and components. But you know, in terms of where we're sitting now, I think we're doing better than I thought we would, and I think we're certainly competitive. And so now it requires us to determine whether, you know, we have something here that maintains its robustness and longevity. And you know, in simple terms, I guess, doesn't fall apart under high wind, which I think is extremely important for us to determine before we, you know, get to the point of full commercialization. And that's one of the reasons we're doing third-party testing. Thanks again to the National Renewable Energy Lab and the CIP grant that we have in order to conduct that down at Intertek.
Thank you very much, Ken. I know that in the chats there are further questions for you, but I'll thank you now because we have to go to the next speaker, who will be Quinton Gargan, as you mentioned before, from Ireland, from Walsers. Thank you very much, Ken, and I hope you will follow us also, because I think there will be a lot of interesting matters for you as well here.
Thank you, absolutely, and thanks for listening. If you have any other questions, don't hesitate to get a hold of us.
Thank you very much.